Okay, so on to our first wet lab of semester 2. And it's a fun one. It involves a subject called colligative properties. And I don't know, I like this subject. I think it's interesting, and I don't think it's a nice mind to break. It's not too mind-bending like perhaps some energy concepts and even orbital theory. A little bit mind-bending, perhaps. So, probably not surprisingly, but when you take a solvent, okay, it's got physical properties, right? It's got a melting point and a freezing point. Tricked you, it's the same thing. The point at which it freezes, the point at which it melts is the same temperature. It's got a boiling point, it's got a vapor pressure, things like that. And probably not surprisingly, if you dissolve something in that solvent, it will actually change those properties, okay? And for the most part, to the first approximation, the changes that happen to those properties are not actually determined by the identity of the chemical that you put in there, so much as they are determined by the number of particles that you put in there, okay? So the change you get on these type of properties with water are, to the first approximation, slight experimental differences, but to the first approximation, you get the same result whether you put sodium chloride in there or you put the exact same quantity of lithium chloride in there, okay? So if a property is affected only by the number of particles, that is called a colligative property. Okay, some text to that, all that. So this is the freezing point, and as we're going to see, freezing point is one of these things that is changed by having something dissolved in it. The freezing point of a solvent is different from the freezing point of a solution made from that solvent. Okay. All right. So in general, okay, dissolving. Something in the solvent can change physical properties of the solution, okay, versus pure solvent. Often, it only depends on number of particles. Okay. Particles of solute. Remember, solute is the thing that you dissolve in a solution, and not the identity. Okay, and that is a colligative property. Okay. All right. So the one that we're going to deal with today is freezing point depression, okay? Could also be described as melting point depression. When you have a pure solvent, say water or ethanol or whatever solvent you have, it has some freezing point, some temperature at which it becomes a solid, okay? If you dissolve something in water or ethanol or whatever it is, that temperature at which it freezes is cold. Okay, that is actually, by the way, why they put salt on roads where you tend to get freezing. Obviously not in Hawaii, but in states where the roads can freeze and then cars can slip all around. That's why they salt the roads, because it lowers the temperature at which you're going to get ice forming on the road. Okay. Some other colligative properties. Boiling point, elevation. Okay, so water or ethanol, isopropyl alcohol has a boiling point. Okay, if you dissolve something in those solvents, their boiling points are actually higher. Boiling point has a little bit of a more complex definition than just the transition of liquid to gas, because there's lots of temperatures that something, for instance, water, if I put water out on a table, at room temperature, okay, it will turn to gas if you give it long enough, right? If you put a glass of water out here and you wait a month, it'll be empty, right? So boiling point has a little bit more complex definition, but the temperature at which something does boil, for instance, with water 100 degrees Celsius, okay, that is a little bit higher actually when you have stuff dissolved in there. So freezing point, depression, boiling point, elevation. There are effects on something called vapor pressure, which we'll learn about later on, so forth and so on. And you can, you can rationalize why this is happening. Let's take specifically freezing point, depression, why you have to get to an even colder temperature before you begin to get that solid. There's lots of ways you can rationalize it, from very sort of hand-waving, cartoonish to more and more theoretical and complex. But you can think of it as the particles are, as a crystal is wanting to form. Okay, a crystal is trying to form because it's gotten to such a cold temperature. Say the water molecules are going to try to form. Okay, the solid particles that are dissolved, or not solid particle, but the particles that you've dissolved in there sort of block access to the growing crystal. Okay, so they block new molecules from coming in, and they do so to a less degree, or they do so to a greater degree, I should say, than they block molecules shedding off the growing crystal. As we'll learn a little bit later on in the semester, a transition like that isn't actually an equilibrium for a short time. An equilibrium, remember, is something that goes back and forth. So as something is freezing and becoming solid, molecules are adhering to the crystal lattice, growing the crystal lattice, but some are also being shed off. Okay? So in any case, the crystals in the solid solute particles that you've dissolved in the solution are blocking access of the solvent to form a solid crystal lattice. Okay? All right. A lot of hand waving there and shouting. Hopefully add some clarity to it. Okay. Freezing point depression. Okay, which from now on we will abbreviate FPD. Okay, is a colligative property. Okay. And it's defined as the freezing point, we'll abbreviate that as SP from now on, of a solution. Remember, a solution implies something is dissolved in it, is less than the freezing point of the solvent. Okay. All right. And sort of real quick, so it's in your notes, explanation for that. As the temp falls, okay, solid begins to form, okay, and solute particles, okay, access to the forming crystal. Okay. All right. And, you know, different solvents do this to different degrees, okay? And so there is something called a freezing point depression constant for each solvent, which gives, gives you a way to calculate how much is this going to happen, okay? Now, obviously, it's going to have to be dependent on how much you put in there, right? The more you put in there, the greater depression you get, okay? So we have an expression. We're going to have an expression of, you know, what's going to be this change in temperature, how much is it going to drop by, okay? And that is going to be dependent on, first, the freezing point depression constant for that particular solvent. Then it's going to be dependent on the concentration of how much stuff you put in there. Okay? The concentration term we're going to use is a little bit different than what we've used in the past. We've mostly used for concentration molarity, moles per liter. Okay? For this, we're actually using something called molality, which is very close to, very similar to molarity. It is defined as the moles of solute per kilograms of solvent, okay? Whereas with molarity, it's moles of solute per liter of total solution. So two little differences there. First of all, rather than a volume of solvent, or solution rather, we're using the mass of the solvent, okay? And there's a very subtle difference, which normally would make absolutely no difference between the two, and that's that in molarity, it actually includes the volume of the solute. Now, most of the time, the things that we make, the volume of the solute is negligible, but that's not always the case. You can add enough solute that it starts to contribute to the overall volume, and in those situations where it's big enough, has to be included in that volume of the solvent. Okay, but this one is only dependent on the moles of solute over the kilograms of solvent. And one of the reasons that this is a better term to use is that the mass of the solvent doesn't change with temperature, but volume of solvent will change with temperature. Things expand and contract depending on what temperature they are. So again, these differences aren't huge. But there is a slight difference. Volumes do change depending on what temperature they're at. Ice and water are one of the absolute exceptions to this. Solid ice, so you're getting down, that volume is actually bigger than liquid water, okay? And thus the density is lower, and thus ice floats, okay? So in any case, we're going to use molality instead of molarity for our freezing point depression. Okay, and we're going to sort of deal with two things today. This the equation that I'm going to put up there and everything, that's going to give you theoretical freezing point depression. Okay, you don't have to do the experiment. If you've got that constant for the solvent you're doing, and you know how much of a solute you put in the solution, you can get a theoretical value for how much it'll change the freezing point. Okay, and we're going to see that that contrasts sometimes to what the actual experimental value is. Okay, all right, so theoretical freezing point depression. Okay, can predict the theoretical freezing point depression for a given solvent. Okay. And that's given by, I've got a bunch of different formulas in this pre-lab today, so I'm actually going to give them numbers. Okay, so this is equation 1. Okay, and so we have delta T, which is by how much is what is going to be the change in temperature of solution versus solvent. Okay, and it gets a subscript F because we're talking about the freezing point depression. If this was boiling point, then that might be a B. And I want to put in parentheses right here that this is the theoretical one. Okay? And that is going to equal Kf, that's the freezing point depression constant for whatever solvent you're dealing with. Okay, and then like molarity is expressed with a capital M, molality is expressed with a lowercase m. Okay, so that guy is the FPD. So how much lower solution freezing point is. Okay. That is the freezing point depression constant. Okay. Specific to that solvent. Okay. And then this is the molality, M-O-L-A-L-I-T-Y of solution. Okay. All right, and then let's put our definition of molality in here. So you've got it in your notes. Okay, is moles of solute, okay, per kilogram of solvent. Okay, all right. And I will make the note that molality doesn't change with temperature. Okay. Molarity, capital M, does change. Okay, a little. Okay, and as an example, I think you can see this. Hopefully you can see this. The freezing point freezing point depression constant actually, I'm sorry, I'm so sorry. Let's just do it this way and write all that junk out. The K of F for water, which you are actually going to need, that is minus 1.858 degrees Celsius kilogram per mole. Okay? So if you look here, kilogram on top, mole on bottom. With molarity, or molality, sorry, it's the opposite, right? So those will cancel out, and when you spit it out, you'll lose your units of kilograms and moles, and you'll be left with just degrees Celsius, which is what you want for a change in temperature, right? Okay, very good. Okay. Now, it turns out that if you have an electrolyte, the situation is a tiny bit more complicated. Okay? What is the definition of an electrolyte? All right, think back, pause the video if you have to think on it. Okay? Okay, you paused it and you're back. Remember, an electrolyte, it's something that causes ions in solution. Okay? And essentially what that means, and it's used a lot of the time simply as sort of a backwards or a roundabout way, honestly, of telling you that you have dissolved a salt. Okay? You've dissolved something that turns into ions when it dissolves. Okay? So a salt, something, a metal and a non-metal mixed together to make a compound. Okay? And the reason why you might even take a moment, maybe you can think about why would dissolving a salt, like for instance sodium chloride, we're going to do today, why would that make a difference to dissolving a non-electrolyte? Non-electrolytes are molecules in general that just simply dissolve and they don't create ions. Why would that make a difference? Remember, on colligative properties, remember colligative properties only depends on the number of particles. So why does an electrolyte make a difference? Pause. And we're back. Worst thing about my teaching and my jokes is I never tire of them, and it's just, I'm so sorry, so sorry. Summer's almost over, guys. Okay, well, the reason why it makes a difference with an electrolyte is it depends on the number of particles. Well, if you dissolve a salt, you're going to get twice as many particles, depending on what the salt is. Or maybe you'll get 3 times as many particles, right? If you dissolve sodium chloride, you're going to get twice as many particles. You put in X number of particles of sodium chloride, you're going to get 2X, okay? If it's some salt that has, magnesium bromide. Okay, magnesium bromide is going to dissolve. The formula for magnesium bromide is MgBr2. Okay, when you dissolve it, it's going to create every single unit of magnesium bromide is going to create 1 magnesium ion and 2 bromides. Okay, so you're going to get 3 times as many particles. So you simply need to introduce something into your formula that accounts for that. Okay, and this is again for your theoretical, okay, not doing the experiment, theoretical, what is going to be the change that we see in freezing point if we dissolve this now electrolyte in solution. Okay? All right. Oops. Okay, so C. Theoretical freezing point depression of an electrolyte. Okay. Remember electrolyte. Okay. Dissolves and creates ions. Okay. So in other words, it's a salt, an ionic compound. Okay. And that means it creates more particles. Chloride, solid, okay. Dissolve it in H2O, minus aqueous. Okay. Double the number of particles. Okay. All right. And so we have to account for this in our formula. Okay. All right, so that leads us to equation 2. So, delta T and it's freezing point depression, but let's go ahead and put in parentheses to remind ourselves this is theoretical and this is electrolytes. Okay, oops. Keep my colors coordinated. Same constant given your solvent, okay? Molality, and then I, okay? Your pre-lab notes for this don't use the letter I, they use the letter V, I believe. Yeah, sorry about that, but if you're in the lecture course, the textbook, and I think most textbook and more common is I. And this, by the way, is called the Van Hoff factor. Okay. And it's simply going to be an integer value for how many particles get created per particle of solid. So the Van Hoff factor for sodium chloride is going to be 2. Nice and simple, not too hard, right? All right, so this is freezing point depression for electrolytes. Okay. This is still the freezing point depression constant. Okay. For that solvent. Okay. Molality. And this guy is the Van Hoff factor. Okay. All right, so for sodium chloride, what's the theoretical Van Hoff factor? Okay. Well, that is going to be 2. Okay. How about, guys, calcium hydroxide? Okay, what's the Van Hoff factor? Theoretical Van Hoff factor for calcium hydroxide. Okay, that is 3. Okay, you get calcium and you get 2 hydroxides. 3 particles for every unit of calcium hydroxide. You may wonder a little bit, why do I keep saying theoretical Van Hoff factor? As we're going to see, and actually sort of one of the fundamental points of the experiment that we're doing today, is that we will find that often the effect of the electrolyte, the effect of this part in an experimental situation is not quite as big as the theoretical Van Hoff factor. Okay? You don't get, I mean, this would imply that if you dissolve in calcium hydroxide, it's going to be 3 times the effect you get if you just put in a non-electrolyte. Okay? And we're going to see that experimentally it is often less. You don't get quite as much impact from that. Okay? And that, by the way, is more so the more concentrated the solution gets. Okay? And the reason typically given for that is that the ions, yes, they dissolve, they create 3 times as many particles, but they do have some interaction with each other. They're gonna bump into each other every once in a while. And when they bump into each other, they might have an association, and they might actually, 2 oppositely charged ions might behave ever so momentarily as one unit rather than, spread out over the billions and billions and billions of particles in the solution. You can see that it'll damper that effect down a little bit. Hope that makes sense. Okay. And the more concentrated the solution is, the more likely they are to run into each other. Okay. All right. Okay. So, note. If you dissolve a non-electrolyte, okay, X molex, okay, dissolves into X molex. Okay, there's no dissolve and create more things. So you could say in that situation that the Van Hoff is 1. Okay? So if you're doing calculations and stuff for a non-electrolyte, you can just you can put in a 1 there, or you can just use equation 1, which doesn't have that that variable in there. Okay? All right. All right. Now, as I said, sometimes the degree of freezing point depression experimentally is less than would be predicted with these formulas that I just gave you, okay? Especially if it's more concentrated, all right? So, how would you do something as challenging as determine the freezing point depression in an experimental situation? That's not too hard, actually. You just need to set up an experiment such that you take a solvent and you cool it down, all the way to the temperature at which it freezes, okay? And then you do it with the solution. You dissolve in whatever it is you're going to do, and cool it down even farther than you did over here, okay? And you determine, and I'll leave that a little bit vague right now, you determine what's the temperature that this one freezes at, and then you compare the two. You take the difference and you've figured out your experimental freezing point depression. And we are going to do that today. Okay, so experimental freezing point depression. Okay. Easily determine freezing point depression experimentally. Determine the freezing point of pure solvent. Okay. Determine the freezing point of solution, okay, and take the difference. All right, equation 3. Okay. Delta T, and that is going to be freezing point depression again, but now it's EXEP for experimental. Come on, Gideon, slow down. Okay, okay. EXPER equals T of F for the solvent, okay, minus T of F of the solution. Okay? All right. As I mentioned before, green here. Shake my green. Oh no, that green is no good. Experimental. Experimental FDP of electrolytes, okay, electrolyte solutions, okay, is often less than theoretical. Okay? And this is because the Van Hoff in the experimental situation, so the experimental Van Hoff factor is often smaller than expected. Okay? All right. And some reasons for that, which I've already vocalized. Ions interact with each other. Okay? Especially when concentration is high. Okay. All right. If we determine the freezing point depression, okay, the difference in temperature experimentally, we can also figure out the theoretical one simply by using equation 2. Okay, we would then have we could then compare the two of them. Okay, and if we figured out the freezing point depression experimentally, we could also come up with the experimental Van Hoff factor. Okay. If we determine experimental freezing point depression, you can calculate the experimental Okay, Vant. Just say Vant. Okay. Equation 4. Okay. The Van't Hoff factor, experimental. Okay. I've just simply solved for this, just rearranged equation 2 for the Van't Hoff factor. Okay, the delta T, still the same freezing point depression constant for whatever solvent it is, and the molality. You did the experiment in the lab, you know what the molality is, and then this is your experiment. Oh, I forgot the F. Experiment. Okay. All right, all right, all right. Okay. So couple more details. One of them is that I don't know if you remember, but I was a little bit vague about determining the freezing point. Actually, how you do that. Okay. And it may seem like, well, shoot, just put a thermometer in the solution, and when it becomes solid, then you read the temperature. Okay. There's a few problems with that. Okay. How do you know when to call it? How do you know when the temperature is changing? Okay. How do you know when it's totally solid? All right. There's another problem that you probably didn't know. When something freezes, the temperature can still change. It can get even colder. Okay. And most things will do that when they freeze, and that's called supercooling. Okay. So the temperature goes down, goes down, goes down, goes down, goes down, and dips down below, and then typically plateaus at some level. Okay, so determining that freezing point is actually a little bit difficult, but fortunately we have a nice solution for it. So what the behavior typically does is the temperature will fall, whatever cooling technique you use. The temperature of the liquid will fall, or the solution will fall and fall and fall and fall and fall. Okay, and it does so typically in a linear fashion. Okay, then at some point it does some dipsy-do. Okay, typically, obviously that's not linear. Okay, but this first part was linear. Okay, and then it'll come up and do its, and then as I said, it'll plateau. Okay, well, a real nice sort of trick for figuring out a fairly accurate freezing point is you find this section of linear data points where over time, I'm sorry, I should have made that clear. You're looking at the temperature over time, okay? Imagine a graph. I'm going to put it up there in a minute. And you look at, you've got this one linear portion, and then when it plateaus over here, it's also linear, okay? Well, if you fit a line to that linear section, and you fit a line to this linear section, and then figure out where they intersect, okay? The temperature at that point of intersection is your freezing point, okay? All right, and I'll give you a picture here. All right, so technique for accurate. Okay. Key is accurate determination of freezing point. Okay. Sticking a thermometer sticking in a thermometer, I should say, into a solution. Yeah, let me. In a solution, okay, waiting to freeze, okay, and then reading some temp, Okay, that can lead to ambiguous and inaccurate freezing point. Okay. Some problems. When exactly do you read the temp? Okay. The temp of the solid, okay, will continue to fall. Okay. And then warm a little. Okay. And this is called supercooling. Okay. And then you have some error associated with your thermometer, of course. Okay. So what you can do is take a bunch of temperatures at a bunch of different at different time intervals and generate a graph such as that. Voila. Okay. So we've taken temperatures. We've started. Probably started up near room temperature, which is 23 degrees, but that's fine. And at certain time intervals, we've taken temperatures. Okay, and the temperature's dropping. Okay, and then you can see it kind of flattens out, dips below. We've gone below. Let's pretend this is water. It's dipped below zero. It's gone down, but then it warms up again, and then it kind of plateaus out here. Okay. So, you're going to do something like this. You're going to do this, what is it, I guess, 3 times. You're going to do it once for pure water. You're going to do it once for sodium chloride solution, and you'll be given data and stuff. And then you're going to do it once for an unknown non-electrolyte. And I'll talk about that in a second while you're doing that one. Okay, but so you're going to take this data, the data that you're given, and then you're going to put it into Excel, okay, and then graph it like that, do a scatter plot like that, okay. You are then going to have to pick the 2 linear areas, okay, so you have to pick some area in here that's linear, and you're going to have to tell Excel which data points to include. Now, for Excel specifically, I myself, in my worksheet, have included some notes on how to do this, okay? If you're using something other than Excel, you may have to do a little bit of investigating. Yeah, I mean, it's not very hard, and I bet everybody watching this knows how to make a trend line with a bunch of data, okay? You've got a scatter plot, and you want to make a trend line. It's linear data, okay? What's a little bit challenging, first of all, is you need to make 2 lines, okay? And not only do you need to make 2 lines, you need to only use parts of the data, okay? So what you're going to have to do is look at it, okay, and decide which part of the data is pretty linear. It kind of dips a little bit here, so maybe I won't use that data point. Maybe I'll just start with this one, okay? And I'll go to, say, like, I'll go to, say, this one, okay? And then I'll tell Excel, generate a trend line for just that, the data in between those 2 points, okay? And so it'll generate a line for those 2 points. Oh boy, whew. It will generate a straight line, which I of course did not do. And then you want to look here. Now this isn't linear, this isn't linear, this is, none of that's linear. You want to find this plateau part, and don't be afraid if it's only a small subset of the data, as long as it's relatively linear. okay? And then you will, you go, okay, well maybe it's, I don't know, maybe it's that points and that points, all right? And then generate a trend line for that, there, okay? And then you'll have it spit out the equation, okay, for this line, y equals mx plus b. And then a second one, y prime equals m prime x prime plus b prime, okay? Two different equations. And then you have to find out where they intersect. And you've done this in algebra at some point and stuff. You may be a little bit foggy, but I'm going to go over it here in just a second. Okay, so let me put some text up here to this. So, yeah, there's a better way. That's sort of continuing from the text that was right here a second ago. There is a better way. Okay. And that is core temps at regular intervals okay, as cooling and after it's a solid. Okay. Decide the before and after, it's really the before and after the dipsy-do, sections of linear data. Okay? Draw a trend line for those sections. Okay? Get the equations. So, you know, Excel a lot of times, right click, add equation or add trend line equation. I forget. Equations and where they intersect. Is your freezing point. Okay, that's a good, accurate way of determining your freezing point. All right. Okay. Now let's pretend these were our equations. Okay, so y equals minus 1. It's going to have a negative slope, right? Y equals minus 1. 0.112x plus 15.164. Okay? Say that was the first one. And then say the second one was y equals 0. I generated these, so they're a little too similar for my liking, but 0.112x plus 0.202. Okay? All right, so how do you find where those two lines intersect? And there are sometimes where, you know, maybe when you add these trends line, it doesn't even continue, the line on your graph doesn't even continue to show that they intersect. But if you extend two lines that are not parallel out, they eventually have to intersect. That's some law of geography. Geometry. Okay, so how do you figure out where they intersect? Well, they're both already set up for y, okay? you know where they intersect, they're going to have the same y and the same x, so just set those two equal to each other. Set negative 1.112x plus 15.164 equals negative 0.112x plus 0.202, okay? And now you've got an algebraic equation with only one variable. Solve for x, and you'll figure out the x where they intersect. But the x is the time that it happened, okay? You don't care about that. What you want to know is the temperature. How do I do that? Well, you take the x that you just found and plug it back into either of the formulas. It doesn't matter because at the intersection point, you're going to get the same y, okay? Okay, and that's how you do it. There's other ways to do it. I think I've had students say, oh, my teacher taught me to add these things or something. I don't know. Anyway, that's the way I was taught to do it, so. Okay, last thing we're going to do. So we are going to, you're going to get, or I will run for you, an unknown non-electrolyte, okay? So now this is something where the Van Hoff factor is 1, okay? And we are going to weigh out a certain amount of it, okay? And put it into water and dissolve it, okay? And so we'll know the mass of it, okay? We don't know its identity. And then we are going to figure out what its freezing point depression is, okay? The experimental freezing point depression. And we'll compare that back to water to get our freezing point depression, okay? It turns out that if we know the mass of stuff that we put in there, okay? The mass of our unknown that we put into our water. And we know the mass of water. We got to know the mass of water. That's important, okay, right? Because we need to know the molality. If you know the mass of solute, and you know the mass of water, and you know the freezing point depression, okay, that you get with that unknown electrolyte, you can determine the molecular, the molar mass or the molecular weight, is what the assignment says, okay? You can figure out I like to describe it as the molar mass of your unknown, okay? And that would, that would give you a hint as to what your unknown might be, okay? All right, so how the heck can you do that? The easiest way is to show you, this is something resembling a very, very elementary, it's not even a proof, it's a derivation. Okay, so determining molecular weight, which I never like, it should be molar mass, but that's fine, of a non-electrolyte okay, solution from freezing point depression. Okay? All right. If we make solution of unknown compound, okay, but we know it's an electrolyte, okay, oh, I'm sorry, it's a non-electrolyte, alright, we will know the mass of solute, okay, and mass of solvent, water in this case. Okay. We can determine the freezing point, depression experimentally. Okay. And then calculate, okay, the molecular weight of the unknown. Okay. How in the world can we do something awesome like that? Okay. All right. Well, you've got your freezing point depression that you've figured out experimentally. Okay. And that equals your freezing point depression constant times your molality. You don't know your molality right now because you don't know the number of moles because you don't know what the molar mass is. Okay. All right. Let's. So let's write out molality. Okay. So we know that it's moles of solute per kilogram of solvent. We're just going to rewrite this formula, but write that out. Okay. So equals Kf times the moles of solute, okay, over kilograms of solvent. Okay, now we're going to do something kind of funny. We can substitute in molecular weight in here. We can take moles out and substitute molecular weight in. Remember, molecular weight, I should remind you of that, or molar mass, is grams of solute per moles of solute. Okay? All right, so how can we substitute that in? Well, I'm just going to put it in there and then see if you convince you that it was a legal move I made. Okay, I'm going to put grams of solute on top. Okay, and then I'm going to put that over molecular weight of solute, okay, times the kilograms of solvent. Okay. That grams of solute over molecular weight of solute is the same as moles, okay? Because remember, this guy here is grams per mole, okay? And it's over grams, okay? So that just translates to moles on the numerator. Does that make sense? Hopefully that does. If not, pause the video and maybe do it for yourself, okay? All right, so that's how I was able to take moles out of the equation and put in grams of solute and molecular weight. And maybe now you can see where we're going with this. We know this because we weighed it out on the balance. We know this because we weighed it out on the balance. That's what we want. We also know that. We know everything in the formula except for the one item that we're after. Okay. Always good to solve for what you're looking for. Okay. Solve for molecular weight of solute. Okay. And now you're going to get molecular weight of solute. Okay, equals the Kf times the grams of solute, okay, over the freezing point depression that you figured out experimentally, okay, times the kilograms of solvent. I lied to you. I apologize from the bottom of my heart. There are 5 equations for this. And that, folks, is the prelude. Okay? Let's go do it. I don't know why I always like to clap before we do an experiment. Just excited. Okay, see you there.